Yeah, so or this morning, I'm going to talk about how to prove things are chi-bounded. And then this afternoon, James will prove how to prove things are not chi-bounded. So at the end of the day, you'll know everything. But I'm going to start off by explaining and motivating a bit what chi-boundedness is. That makes it more exciting to know everything. So basically, the idea is you have chi and omega, which are dual parameters, and clearly, my space. Clearly you have chi of G is at least omega G or all G. And chi-boundedness is trying to ask like, okay, we have this lower bound. Is there any way we can also get like an upper bound here? So the most naive question is, do we always have equality? And that I think given like a minute, everyone could, who hasn't seen it already, which is probably a minority of you, could draw a counterexample to and find a graph whose chromatic number is bigger than its clique number. So for example, you could take like C5 or indeed any odd cycle or its complement. And that's really the real answer. So again, probably a lot of you know, there's the theorem 6 by Chudovsky, Seymour, Robertson, and Thomas, which has been since known as the strong perfect graph theorem, that if chi of G is bigger than omega G, that implies that G or G complement contains as an induced subgraph a odd cycle of length at least 5. And this also gives me a good opportunity to say my regular disclaimer. I'm trying to get out of the habit of assuming every containment relation is induced subgraph, but I'm not great at it. So throughout the talk, if I say contains and don't specify, I mean contains as an induced subgraph. And also I'll be using the language like to say that something is H-free if it doesn't contain H as an induced subgraph. I'm going to do my best to always remember to say as an induced subgraph because we're in mixed company, but I'm not actually like historically great at that. So I prefer to warn you in advance. So equality doesn't work. So we then try to maybe make this a bit weaker and think instead like, okay, we don't have equality, maybe we can have that there exists some F so that type G is at most that function of omega. And that's also not true, but now it's getting into territory where probably you can't come up with a counterexample in 30 seconds because you would need to be able to demonstrate that for every that there's some graph with bound like some constant clique number and arbitrarily high chromatic number, and that's a bit annoying, but we've had several open problems about it, so you probably know that it's not true. And indeed there's exist constructions for triangle free graphs. The chromatic number as big as you want it. And that's like a theorem from the 1950s. Various people did it, including like Zykov, Tutt, Michalski, Kneser. This is essentially the subject of James's talk, so I'm not going to discuss it much further. And, so we know this is false, but it's actually even false for like like in a bigger way. So this showed like it doesn't work for triangles. We actually can do even more by saying there's a beautiful theorem of Erdős, which is that you can get graphs without any short cycle with arbitrarily big chromatic number. Yeah, sorry to burst your bubble. This uses probability theory, as do many proofs within chi-boundedness. Actually, that's a part of what I like about chi-boundedness is because it's kind of at the intersection of like structural graph theory and extremal graph theory, and often proofs kind of use techniques from both worlds. So it's quite nice if you like to collaborate with like new friends. You can actually like make friends outside of your community and sometimes make really nice progress. So I'm not going to give you the proof, largely because I was asked to prove this during my qualifying exam, and that's like a horrible memory for me. I did get that question wrong. But basically what you do is you take the random graph GNP and like fine tune the value of P so that there's never a big stable set. And since trivially like chi is going to be at least number of vertices over alpha, you know that if there's no big stable set, the chromatic number has to be pretty big. And then you also kind of have optimized this value to ensure that there aren't too many short cycles, which you then do through like scary probability and counting. And so there's not a lot of short cycles, so you can just like delete one vertex from every short cycle, and you haven't brought down the chromatic number by too much because you haven't deleted the vertices. And that gives you the result. But like, for me to actually prove this, I mean, it's not bad for anyone who's like comfortable with computation, but I would never. And also it's James's responsibility. So kind of, I mentioned you had the perfect graph theorem, which was, this statement was conjectured in 1960-ish by Berge, actually at a workshop. So I guess don't feel too bad if you didn't make any progress on your open problems, because this took like 50-ish years. But this was a really popular problem. And there are other problems within graph theory that kind of fell into this framework of understanding chi and omega. Like, for example, you can think of Vissing's theorem in this way because that gives you a relationship between the chromatic number and the clique number of line graphs. And so kind of inspired by all these ideas floating around, in the 1980s, Gyarfas formalized this framework and sort of posed some open problems in this way. So the definition, which is from a beautiful paper of Gyarfas from the 80s, where he kind of started this whole chi-boundedness field, that class of graphs is chi-bounded if this F, so that if the that function f in terms of the clique number actually bounds the chromatic number for not just all graphs in that class, but we kind of want to take the downward closure in terms of induced subgraphs, basically, because otherwise you can get kind of screwy things if it's not closed under induced subgraphs. So for all and so to rephrase the previous few theorems in this language, basically both of them imply that the class of all graphs is not chi-bounded. And in particular, the class of triangle-free graphs is not chi-bounded. The graphs with no short cycle for whatever your definition of short is not chi-bounded. And indeed, we can rephrase the Erdős thing in a nice way. So it's kind of a rephrase / corollary to. Actually, maybe I want to write it here. So So I'm going to use the new definition. I'm going to use the notation forbid H to be the class of graphs with no H-induced subgraph. And I'm using that language. Erdős's theorem implies that if forbid H is a chi-bounded class, then H is a forest. Because basically if H weren't a forest, then if you look at all the graphs not containing H, all graphs of sufficiently high girth don't contain H, because H has some cycle that actually has like a finite length. And for the next few minutes, I'm going to talk a bit about a nice conjecture of Garfash. Hopefully no one's colorblind. That is the opposite direction. So the converse is conjectured by Garfash in this paper from the 1980s and independently by Sumner a few years later. And this conjecture is largely open in the sense that if you spend like a little bit of effort drawing a forest that's annoying looking, it's probably open for that forest. But if you like spend not a lot of effort and like if I say made you like draw these things in ticks and you don't like using ticks, then there's a solid chance that the tree you came up for, it's known for. I can actually say that a bit more formally. I just don't really want to get into all the known cases, but like basically paths you can do. If you throw on a star at the end of a path, you can do that. All trees of radius 2 work. And then sometimes if you have a tree of radius 3 that's like extra nice, it still works. And these are like all like actually fairly hard papers. And then the big thing was that you can, if you have a path and you throw on a star at both ends, that still works. But I don't really, and then there's like a couple other random trees for which it's known for. But we're on the whole like very far from proving it in generality. So I want to talk a little bit about this result that it's known for paths, because that one's actually nice and it gives you a tool that's used in lots and lots of other proving other theorems related to chi-boundedness and also beyond chi-boundedness. Like this technique is used in some of the recent proofs for cases of the Erdős-Heinel conjecture. If you don't know what the Erdős-Heinel conjecture is, you don't need to, just know it's a fancy problem people like. So sort of call it. So it's known in the literature. We're very creative about giving names as a Garfash path argument. And you'll see what it is through proving that paths are chi-bounded. So so the way he proves it is by kind of, he's going to like grow a path in your graph that's always like pointing to like growing towards where the high chromatic number part of your graph is. And kind of more space. Get a lemma that, so if you have a graph, so if you let G be a graph and you let C is the maximum over all V in of G of chi of NV. So the maximum chromatic number of the graph that any vertex sees. Throughout this talk, I'll be conflating graphs and sets of vertices when I write chi, because everything is induced anyway. There's no possible other containment relation in the world. So that's fine and safe to do. So you have the maximum over all the chromatic number of all the components, and you want to say that if pi of g is sufficiently large, then every vertex in G is the start of a K vertex path. And that's the theorem for all K. So large enough is as a function of C and K. Large enough means greater than equal to F of CK. And the way we're going to prove that is no probability theory. We're going to do induction on K. Clearly this works when you don't have a path of like say one edge. You can't have big chromatic number. So let's just, so we're gonna fix C, sorry, induction on K, so then we can assume, so then F of C K minus 1 is defined. And then I'm going to set F of K equal to F of C K minus 1 plus C plus 1 just for luck. And now I want to say I have a graph that has more than uses more than this many colors. So then what do we do? So we want to prove that it actually satisfies this property where everyone starts a vertex, is the start of a PK. So we choose some vertex. We're going to look at its neighbors. Its neighborhood uses at most C colors. So after we delete it, we still have a lot of colors left over. So I'm going to take a maximum component in the rest of the graph. And that component has to have at least F of C K minus 1 colors. And also, since we're assuming pi of G is F of CK, we may as well assume that G is connected. Can you see it, or is it too low? I'll get rid of the lemma statement. And so then, since G was connected, and this is a maximum chromatic number component, there at some point has to be some edge going from this to the neighbors of the, maybe call it like X, Y. And so then we're going to look at the graph. So more colors.
Why can you assume connected?
Because if not, we can do it for each component. Within G has big chromatic number.
Have an isolated vertex, how can there be?
Well, yeah, but then if I ignore that, there is some component in G that has.
Statement said about some component. I thought the lemma says every vertex has an induced. So.
Oh, sorry. Yeah, I think I made a mistake on the statement then. Yeah.
Did have degree 1 vertex. Ah, no, okay, connected.
I mean, we could have a degree 1 vertex, but
You know,
Here,
then okay.
it
Then
still built the path. Yeah, sorry. Good point. Uh, yeah, isolated vertices do not tend to be the starts of long induced paths. And so now we're going to do induction on this graph. So I'm going to call this G prime, which was a maximum chromatic number of component of G minus a neighbor V. So we apply induction to the graph induced by G of G prime union X. And that, since we only ever deleted at most C colors, is still going to have chromatic number at least this. And therefore by induction, we can get a path starting at X of length K minus 1 within G prime. And so adding in back V gives you a path on this thing. Yeah, so that's quite cute, and essentially like no proof is ever short and cute again. I'll show you maybe quickly why this implies that it's chi-bounded. I think it's fairly clear. Maybe I will pause for a minute and let you think, and then I will tell you. And also use this opportunity to ask a question. Oh, I forgot to mention, if you ask a question, you get a cookie, because I believe in bribery, but you have to eat it outside because there's rules.
Can you lift the board up, please?
Hmm?
Can you lift the board up?
Yes.
Thank you.
Oh, but I lifted it so that you can no longer see the lemma statement that I wanted to think about why it implies the full theorem. So I think that was, it's actually not really possible to lift it up because the lemma statement's at the bottom. But I think you can ignore this for print. Oh, you can swap. Yeah, that's a good point. Yeah. Give you a second.
That wasn't the question.
Curiously.
Wasn't the question. He said you can swap.
Yeah, I know, but I make the rules, right? Like, it wasn't exclusively questions. It was just things I find helpful to giving a talk. Yeah, so basically, the reason this implies the full chi-boundedness thing is that you do induction on omega, and then if you look in the neighborhood of any vertex, its clique number has to go down by one less than like it's cannot have a maximum size clique in the neighborhood. And so for this reason, you actually get that there's a choice of C that depends on omega that's defined, and you can just apply the lemma and win. Is that clear? Hmm? Okay. You look skeptical.
No?
Can you re-explain why the lemma implies a theorem?
Sure, yeah. Okay, thank you. Yeah. I guess people don't like cookies, so I shouldn't throw one at you. But yeah, so we're going to do induction on omega. We're going to let C equal the maximum of chi of G prime over all G prime with omega G prime less than omega G and PK free. And basically by induction, we know that this is finite. And then, yeah, that's your C. Yeah. Yeah, because I'm lazy, I'm going to give two more examples of like kind of the last cute things that exist in chi-boundedness, or at least in Garfach-Sumner. And then give you a short break to think about them. So kind of our second tool, which I'm never going to use in a serious way in this talk, but is actually like one of the most important tools, is just using Ramsey as your friend. And again, because I'm lazy, I will give you just the statements of some theorems. So forbidding K1T, so a star is chi-bounded. And also forbidding kind of a star where you add a path on the end is also chi-bounded. So I'm going to call it B LT, where BLT is you take a path of length L and a star with T leaves, and you identify one of the ends with the roots. So 1, 2, L, and then you'd get 1, 2 T vertices. So this is proved just with a pretty direct application of Ramsey theory, and this is kind of that argument plus the Garfach path argument you just saw. And just to hopefully get people to be slightly more awake, I'm going to give you like a 4-minute break to think about this. I'm not going to ask you to do it at the end, but I personally find it really hard to just listen to someone talk for an hour. So, and I find it hard to talk for an hour. So I'm letting you think about this or just otherwise take a break for the next 4 minutes. I mean, you can stretch. I don't really I'm not making too many rules. You can also like take this opportunity to ask a question and earn a cookie. I can see now I got one. Oh. Then I chose cookies and not something like more heavy.
So, this theorem that you said down there, what is, which value of K for OK?
For okay, at least one. So you don't have an odd induced cycle of length at least in your graph or its complement.
What are graphs for this, for which this is not true?
What do you mean? Like a graph that has
Yeah, just a
an no, a complete graph doesn't have it, but like a C5 has an odd induced cycle. I think maybe I'm just, because I'm stating the perfect graph there in a weird way, basically. Maybe it's easier. And so on. So if you just take like any of those cycles and add anything else to your graph, then that's a graph that's not perfect. I mean, the way I've stated it, the converse is not true, of course, because you could just add in a big clean. Yeah, I meant to like play some music during this break, but like technology failed me. People were not asking an annoying question. Okay, so it's been about the amount of time it takes for Larry the fox to let, not Larry the cat to chase away a fox. So I think you should, well, I'm not going to let you take any more break. So I think I'm just going to tell you the answer, which maybe you knew it or not. So basically the reason is because you can just get a bound on the maximum degree. You look at a max degree vertex, if it's huge, then you can apply Ramsey on it. If there's a huge stable set, you have an induced K1T. And if there's a big clique, then, well, you have a big clique, so. And that gives you the result. And in fact, due to the way we can bound Ramsey numbers, we can get that this is actually polynomially chi-bounded.
What does that mean, Linda?
What does that mean, James?
Do I get a cookie for answering?
Yes.
It means that your chi-bounding function is polynomial.
So F's polynomial.
Yeah, fifth polynomial.
Oh, sorry, yeah. Yeah, it means that your chi-bounding function is polynomial, and basically for everything I've stated, we don't know whether or not it actually is polynomial, but for like all of these theorems on the board, pretty much uniformly the chi-bounding, well, okay, not paths and stars, but like everything else, the chi-bounding function is like really like crazy Ramsey constants that are like 2 to the 2 to the 2 to the omega. And we don't actually, it's really annoying because we don't actually know at all. Like these could all be polynomials in omega, but we have these like crazy tower functions of 2. And for a while, we did not know whether or not there in fact was any chi-bounded class that wasn't polynomially chi-bounded. But then Sophie Sperkel, Patrick Humph, Alvaro Coronero, and Ben Moore did some breakthrough, and then James very annoyingly used this breakthrough with to show that such classes actually exist. So we no longer live in a nice world where we can expect there always is polynomial chi-boundedness, and it's James's fault. But since it's his theorem, I didn't really want to talk about it.
That's what the sad face is.
That is what the sad face is. Yeah. So yeah, speaking of polynomial chi-boundedness, I wanted to give a few remarks on the path proof. So for any of you who has a background in extremal combinatorics or just for other reasons doing recurrence relations, you can see that this gives an exponential bound on the chromatic number. So the F we get out of this is something exponential in omega. And that's a bit annoying because paths are pretty simple. So like maybe they really should be polynomially chi-bounded. And in fact, I should get an eraser so I can write things as I say them. But Garfash in the paper where he proved that it's paths gave a lower bound for the growth of the function, which was like something polynomial with like a decently high degree depending on the number of vertices, but not like anything crazy. And since then, people have been kind of interested in figuring out better bounds for this. But it's been really terrible. Like even for so for P4 you can do it because they're have a really nice structure. So they're actually perfect graphs. So their chromatic number is equal to omega. And then for P5, like you're just dead. And a open problem that I quite like besides P5 is to then kind of, well, P5 is too hard, which is quite sad. But like, what if we, instead of trying to bound the chromatic number of P5 in terms of its largest clique, we try to bound the fractional chromatic number in terms of its largest clique? Can we then get it to be a polynomial? And it's really annoying because we still don't know how to do it, even with this like rather big relaxation. So I'm gonna quickly kind of write down some of the results that I mentioned in words. And I have a word. So So we have a theorem from Kerfash that F is at most O of like 2 to the omega, and at least I'm going to get it slightly wrong, but something like omega to the K plus 1 over 4, something linear in K. And this has since been improved by a few people. Let me find my notes on it because I always forget people's names. Yeah, so since Gravier, Hong, and Maffrey got this bound to be a bit better, so it's weird. Gravier, Qin Huang, Maffrey. And even for P5, we're still kind of like not sure what the truth is. I think most people.
Was that better, Linda?
Is this better?
Oh, because this is not a big O, that's why it's better. Yeah. Thank you.
Go on.
No. Yeah, and so even for P5, we're kind of screwed. Like, so if we have K equals 5, you can plug in what you get with these bounds, but we also, since that's sort of a niche case, there was like an old paper from a while ago that says F to 5 over 7th, 3 to the omega, which is kind of obscure, which was from Esprit, Le Monde, Maverick, and Morel. And then they got it down to omega to the log omega, so like kind of quasi-polynomial. That was Scott, Seymour, and Sperkel, 21. And it's still somehow, it's annoying. We can't like, on P5 is like a very small graph. Like we somehow, if we could do it, we should. And in particular, I should mention that, again, Erdős-Heinel, which is a problem I won't tell you about. If you're polynomially chi-bounded, that implies you have the Erdős-Heinel property. And this is like a big fancy problem people care about. So if you prove that, like, you know, all paths are like forbidding any path is polynomially chi-bounding, that would actually give you also a big breakthrough for this other famous problem. Yeah.
I have a question about the theorem from I feel like if I plug in K3 into the upper bound, that I then get something
Yes.
better.
Yeah, you need.
You need 2 to the O omega instead of O to the omega.
I think this didn't apply for it. They had a different bound for K equals 3. Yeah. Yeah, sorry. Yeah, they had like some, like they needed to assume K was at least 3 to get this bound. Sorry, K is bigger than 3 to get this bound, sorry. Yeah. Um, Yeah, so anyway, so basically by some kind of like computer sciencey-esque proof, you can expect that proving polynomial chi-boundedness of a graph class is hard, because then that means the graph class has the Erdős-Heinel property. And then there's other mathematicians who are trying to prove graph classes have the Erdős-Heinel property. So probably doing something that implies that is not super easy. But for P5 free graphs, we know it has the Erdős-Heinel property. And it's not easy, but we know it. So it really feels like this, we should be able to show that, I mean, we understand P5 free graphs pretty well, so we really should be able to show that F can be a polynomial. But as I said before, we can't even do it if instead of omega, if instead of the chromatic number, we're looking at the fractional chromatic number, which is not something I will define, but essentially the fractional chromatic number is equal to the fractional clique number, which is at most the chromatic number and at least the clique number. So when we replace chi with the fractional chromatic number, it gets strictly easier because it's less. And so basically, we're looking now just at this gap instead of at this entire gap. And so that's everything I wanted to say about the Garfish-Sumner conjecture, because it's basically too hard. I mean, it would be nice if someone proves it. I think it's probably true. So I wanted to talk a little bit more about some other chi-boundedness stuff, introduce some methods. But please stop me at any point, because I'm more invested in you like understanding and following this talk than I am in actually like covering all the material I planned. And
Linda, what did they do different in this breakthrough, this omega to the power of omega?
oh, I did not read the paper. Do you know?
I've read it, but I don't remember.
Yeah.
So, but they didn't use anything particularly new, or?
It wasn't like this path argument. Somehow they look at like low chromatic cut sets.
So basically, Garfish-Sumner, this is just one more modality you could think about chi-boundedness in, which are graph classes defined by forbidding just one thing. And people look at lots of other stuff. So there's like geometric, like graph classes defined by geometric things that people prove are chi-bounded. I don't talk about this because James promised he would. So I'm going to talk a little bit about now the case where if instead of just forbidding like one abstraction, you're forbidding an infinite amount of abstractions. Which gets you out of this, kind of lets you escape from this trap that Erdős set, where you have graphs with arbitrarily high chromatic number. Because if you're forbidding an infinite amount of things, you can just get rid of like everything long enough, or like so just to kind of recall, one way of writing this theorem from Erdős is, so if you're like if you're forbidding a finite set of graphs, so like H1, H2, up to HK, and if that class is chi-bounded, that implies that for some I, one of the graphs is a forest. Because if they all had cycles, then again, this is a finite amount of things, so you can just choose some girth that's a bit bigger than any cycle contained in these, and then apply this Erdős random graph construction to get a counterexample. And so kind of motivated by this, and also again, this perfect graph theorem where we're forbidding all odd cycles of length at least 5 and their complements, Garfush made a couple conjectures about what happens when you forbid odd cycles. And I'm out. Sure. So forbidding CK for three and odd, we want to specify at least 3 because otherwise we're forbidding triangles, which is kind of an easier case. So forbidding odd cycles, forbidding all long cycles, and then finally combining the two and forbidding long odd cycles. And all of these results have been proven in like a succession of paper, which is actually quite cute because the team of authors just kept adding in one more co-author and then getting the next result in the conjecture. So the first one, yeah, was the odd one. So that was Scott and Seymour in 2016. And then they got the long holes for by adding in Maria Chudnowski. So it's Maria, Scott, and Seymour in 17 in the next year. And then there was a little bit of a gap. And then Sophie Sverkel came along. And so now it's, sorry, Chudnowski, Scott, Seymour, and Sverkel in 20. And these have since been unified into an even stronger result, which is theorem for all PQ, forbidding CK such that K is congruent to P mod Q is bounded. And that well, they got rid of some co-authors for that. That's Scott, and that's back to just the beginning of Scott and Seymour in 2019. There's something. I think I'm doing something screwy with when they got published versus when they were on archive. So slight, all the years are plus or minus epsilon. And all of these proofs kind of have a bit of techniques in common, which if I have a bit of time, I'll show you. I also want to mention, so we're talking a bit about odd cycles. Okay, I already told you about P mod Q, but there was like some reason to believe P mod Q should be true, because before that it had also been done for even cycles, so 0 mod 2. And that was done really by purely structural methods. Like they got a really big structure theorem for the graph class. Very, Jesus, there's a million co-authors on this one. Chudnowski, Have, Reed, and Seymour. That so every even whole free graph, so no even induced. Cycle G has a vertex, so that that vertex neighborhood can be partitioned into 2 fleeks. So that immediately implies that your chromatic number is at most 2 omega, because you're not gonna see a maximum size clique in your neighborhood. And so you know that if you have a coloring of the rest of the graph, you do induction and you delete this special vertex. So you've colored this and now you have vertex and you're looking at what graphs it sees. Well, each of these can use at most, like you have 2 cliques, they're of size at most omega -1 and omega -1. So you're seeing at most 2 omega -2 colors. And so if you want to color it with like say 2 omega colors, you always have something left over. And it was also shown for like 0 lot 3 cycles before this by Bonamy, Charbit, and Thomasay. But like all of these kind of are like purely like chi-boundedness proof. We don't really understand the structure. And like this is the one where like we really got chi-boundedness incidentally, like we proved something harder about the structure. When I say we, I mean not me at all. I was not involved. And so kind of motivated by this, like there's been a few other questions floating around about like how we can induce like forbid cycles and get chi-boundedness. So I've seen Vaidi Sivaraman ask like, okay, what if we forbid all the prime length cycles above a certain length? It seems hard. And then there's various other questions. So we know like, okay, we're forbidding some cycle lengths and it's a relatively sparse sparse set of integers because they all like have to satisfy this P mod Q. So maybe other sparse sets of integers would work as long as they're infinite, but like this seems really hard and I don't think our current techniques work well for this because we're really like using that that the gaps are all the same between the cycles you forbid. Yeah, it looks like I ran out of time, so I'm not going to tell you how these proofs work because I mixed up when I started. But yeah, they all have like quite a cute technique in common and it's just kind of extending on it. And yeah, I'll just maybe like leave the last 5 minutes for questions instead of starting something else to confuse you.